In this video, we are going to graph rational functions based on their properties. So let's do a short recap. We have a removable discontinuity, which we also refer to as a hole. It is a point on the graph that is undefined, and it's caused by having a common factor in both the numerator and denominator. So for example, if I was to graph this function over here, it actually would look like a straight line. And the reason is because if I was to factor the numerator, it would factor into x minus 1 times x plus 1, because it was a difference of squares, divided by my denominator, which is x plus 1. The entire x plus 1 factor on top and the x plus 1 factor on bottom cancel each other, leaving us only x minus 1, which is actually represented by this straight line. If we were to take what was canceled, the x plus 1, and we were to set it equal to 0, and we were to solve, we would get x equals negative 1. That would actually represent a hole where x was negative 1 on the graph. It actually would create what we could call a jump, or it is a hole in the graph, which means that one specific point is undefined. Everywhere else is a defined coordinate point, except at the point which we would say negative 1, negative 2 is undefined at that specific point. And then we have a vertical asymptote. That is where a hole is something that canceled. A vertical asymptote is whatever's in the denominator that is set equal to 0, because we know that a denominator can never equal 0. It is undefined. So, for example, if we take this equation over here and we were to look at the denominator, nothing cancels, we notice, so there are no holes. And if we take the denominator, which is x plus 1, and set it equal to 0, we'll get x equals negative 1. That is the vertical line of x equals negative 1. And then we would do the same thing on this side. If we were to factor the top, it'd factor into x minus 3 times x plus 3. And on bottom, it would factor into x minus 5 times x plus 2. No factors cancel, so there are no holes. And therefore, if you take the denominators, which is x minus 5 and x plus 2, and if we were to set them equal to 0, we will get x equals 5, and we will get x equals negative 2. And that would represent two imaginary vertical lines that are what we would call a vertical asymptote. The graphs cannot cross these vertical asymptotes. And now we have something new called the horizontal asymptote. This is actually created when the x values are heading to infinity and negative infinity. So we're not worried about what's going on here near the origin. We are looking very, very far away as it is reaching out to infinity, and as it is reaching to negative infinity of a graph. What's happening when x gets very, very big? We want to know what is the y value approaching. Be really careful about this. We are only wanting to know what it's approaching. It may not hit it, but it's going to get very close to it. So if you think of it if I was to graph this, if you look at this left-hand side, this is a window that is really close to the origin. We're only going from negative 3 to 3. And this is what the graph would represent. It is heading up towards high and low. And then what we're looking for is eventually where it's heading towards infinity and negative infinity. And then I took the graph and I made it a little bit bigger from negative 6 to 6 of a window. And then from negative 12 to 12 of a window. If you look, it is going very, very close towards the x-axis in both directions. And so if you think of it in terms of, let's represent x to be negative 100. Therefore, 1 over x is going to be 1 over negative 100, which is going to be a negative 0.01. And then if we said that x was 100, therefore 1 over x would be 1 over 100, which would be 0.01. Or if you think of x as being negative 10,000, that means we would have 1 over negative 10,000, which would be represented by negative 0.0001. Or if x was 10,000, then it would be 1 over 10,000 on the graph, which is 0.0001. So if you think of the point of 100, 0.01, or even 10,000, 0.0001, when x is getting really, really big, y is getting very, very, very small. However, y will actually never reach 0. It could get very close. You could have 0.00000000 and literally keep going forever, 1, but it'll actually never reach 0. And so what we're saying that as it's approaching, the y value is actually approaching y equals 0. That is actually a horizontal asymptote, and it is technically an imaginary horizontal line that the graph in around the origin, it actually may cross it. However, we're not worried again about around the origin. We are wondering what's happened when x is very, very, very big and very, very, very negative. And we're wanting to know, where is the graph? Where is it heading? And there are rules to determine what that is. So these 3 rules. First, if the degree in the denominator is higher, then the horizontal asymptote will always be y equals 0. So for example, what you're going to do is you're going to find the highest degree of the numerator, and you're going to find the highest degree of the denominator. The numerator has a degree of 1. The denominator has a degree of 2. Because the denominator has a higher degree, therefore the horizontal asymptote is going to reach y equals 0. Again, in this, if you have x squared on top, but you have an x cubed on bottom, the degree is higher on bottom. So again, no matter what numbers are in front, it will always reach a horizontal asymptote of y equals 0. Same thing on this one. Your highest degree in the numerator is x to the 4th. Your highest degree is an x to the 5th. So again, because your denominator has a higher degree, then the horizontal asymptote is going to be y equals 0. Over here in red, this is called a limit notation, and this is just another way to write it. As the limit of x approaching infinity, basically as x is getting very, 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 very big, then an equation that has a denominator that has a higher degree, it will reach the number. It won't hit 0, it will approach 0. Second rule, if the degree is the same in the numerator as the denominator, then the horizontal asymptote is y equals the leading coefficients. For example, in this rational function, the highest degree in the numerator is a 1, the highest degree in the denominator is a 1. Because they have the same degree, then you will look at the leading coefficients, and so therefore the horizontal asymptote will be y equals 5/4. It will represent the coefficients that are in front. Same thing on this one. You are looking for the highest degree in the numerator, the highest degree in the denominator. They are the same. They are both x squared. So therefore, the horizontal asymptote is going to be y equals -2, because think of it as -6/3. You take the coefficients and then reduce. Same thing in this one. Your highest degree is a 3, and on top and bottom, because they are the same, then the horizontal asymptote will be the leading coefficient. In this case, it is a 1, because that is a 1x cubed over a 1x cubed, and so the coefficients will be 1. Same thing, limit notation as x is approaching infinity, because they have the same highest degree, then you're looking at the coefficients, which would be 3. That's supposed to be 3. That's supposed to be 3/10. And last, if the degree in the numerator is higher, then you actually, this is where you could either say the horizontal asymptote is infinity, or you could say that there is no horizontal asymptote. So for example, the highest degree in the numerator is a 2, but in the denominator it's just a 1. So therefore, the horizontal asymptote would be infinity. Same thing here. In the numerator is an x cubed, but in the denominator is an x squared. So again, it would be an infinity. And then on top you have an x. On bottom you can think of it as an x to the 0. So therefore the top is going to be bigger. And again, so it would be infinity. And this is again the limit notation. Because the numerator has a higher degree than the denominator, it is going to approach infinity. So now we are going to graph these rational functions. So beginning with the first one, you're first going to look and see if there's anything that you can factor out. The only thing I do notice is at the top we can factor out a 2. And we can see if there's anything that will cancel from that, which it won't. There's an x minus 3 at the top, but the x plus 1 at the bottom, so they will not cancel. So the first thing we're going to look at is whole. So again, we're going to ask, is there anything that cancels? It does not, so there is no whole. The vertical asymptote is where you now take the denominator and you're going to set it equal to 0. And so you'll get x equals -1, and so that will be your vertical asymptote. So I'm going to go ahead and go to -1 and actually go ahead and graph my vertical asymptote. Next, horizontal asymptote. This is where you're going to look at the highest degree on top and bottom. They have the same degree, and so you're going to look at the coefficients. 2 divided by 1 is 2, and so the horizontal asymptote is going to be at y equals 2. So I'm going to go ahead and draw that. Next, y-intercept is where you plug in 0 for x. So I'm going to plug in 0 for x, and I will get 2 times 0. I'll get 2 times -3, which is -6, over 0 plus 1, which is 1, and so I will get -6. So this is the point, 0, -6. The x-intercept is where I'm going to plug in 0 for y. So I'm going to get 0 equals 2x minus 6 over x plus 1, and I'm now going to cross multiply. So I'll get 0 times x plus 1 equals 1 times 2x minus 6. 0 times anything is 0. And then solve. I'm going to add 6 and divide by 2, and I'll get x equals 3. So my x-intercept is going to be 3, 0. I'm going to go ahead and plot these as well. So 0, -6 is going to be down here, and then 3, 0 is going to be right here. Now, domain and range. The domain is going to be everything except vertical asymptotes and holes. The range is going to be everything except horizontal asymptotes and holes. The hole needs to be the x value, and for the range, the hole needs to be the y value. And so the domain is going to be everything from -infinity to -1, because that is my vertical asymptote, and then from -1 on to infinity. The range is going to be -infinity up to 2, because that is my horizontal asymptote, and then from 2 to infinity. And now in this case, I'm going to go ahead and graph. Now, because I already have these 2 points, I know that these points are going to look something like this, to where they're heading towards the asymptotes. And I am assuming that it's probably going to happen up here, because normally rational functions, not always, but normally they are diagonal of each other. But if we take a point, like let's say -2, and plug it in, we'll get 2 times -2 minus 3 all over -2 plus 1. So we'll get 2 times -5 is -10 all over -1, which is a positive 10. So if I plug in -2, I actually will get 10, which is way up there. So I think it is going to represent something that looks like this, but the best way to check is to either use your calculator or Desmos. And if you're to graph the Desmos, you will see that it does go bottom right and it does go top left. Next, what we need to do first is see if there's anything that factors. So we do know that in this case, we will have an x plus 3 on top, and on bottom we'll have an x minus 3 times an x plus 3. And I do notice that an x plus 3's cancel. That is going to represent our whole. And then what is left, the x plus 3 canceled, so there's going to be a placeholder of a 1. And on bottom, there's going to be an x minus 3. This is what the graph is going to end up looking like. So first, the whole. You're going to take what was canceled, set it equal to 0, and you get negative 3. So I know that my whole is going to be at negative 3, but to find the y value of the whole, you're actually going to plug it back into your final answer. Plug into final equation. So if I do that, I'll get 1 over negative 3 minus 3, which is 1 over negative 6. So I know that that is going to be my whole. So at negative 3, negative 1, 6, there's going to be a whole right there. Vertical asymptote. This is where you take your final equation and look at the denominator, which is going to be x minus 3. Set it equal to 0, and so you'll get x equals 3. So therefore, at 3, I'm going to go ahead and draw my vertical asymptote. So that will be represented. And now horizontal asymptote. This is where you look at your highest degree. The denominator has the bigger exponent, and so the horizontal asymptote is going to be y equals 0. So I'm going to go ahead and draw my y equals 0 asymptote. Next, y-intercept. I'm going to plug in 0 for x. I can plug it into my final equation. So I'm going to get 1 over 0 minus 3, which is negative 1/3. So 0, negative 1/3 is going to be there. By the way, negative 1/6 actually should be more like there. Okay. X-intercept. It is where I'm going to plug 0 in for y. And because of the horizontal asymptote at 0, there's a chance there may not be one. But let's go ahead and check. So I'm going to get y, 0 equals 1 over x minus 3. I'm going to cross multiply, and I'll get 0 times x minus 3 equals 1. 0 times anything is 0, and we get z equals 1. 0 can never actually equal 1, so therefore we are not going to have an x-intercept. The domain, remember, is everything except vertical asymptotes and holes. So we have two things going on. So we're going to have everything from negative infinity to negative 3, which is a hole, and then everything from negative 3 to 3, which is where I hit my vertical asymptote, and then everything from 3 to infinity. You have to break it up into all the x values until you hit negative 3, and then all the x values in between, and then all the x values after 3. The range is going to be everything except horizontal asymptotes and holes. But be careful, this hole needs to be the y value of the hole. So the range is going to be everything from negative infinity to negative 1/6, and then everything from negative 1/6 to 0, where you hit the horizontal asymptote, and then everything from 0 to infinity. Again, the range, you're looking at the y-axis. So you're going to go up until you hit negative 1/6, and then from negative 1/6 to 0, and then after 0. Now we're going to graph. Now because of these points, we do know that it's going to reach this asymptote to that asymptote. And I believe it's going to hit probably in the top right corner because they are normally diagonal. But if I plug in 4, like if I choose to plug in 4 minus 3 is 1, which is 1. So when I plugged in 4, I actually get the point 1. So I am assuming that it is going to reach these asymptotes from this side. To double check, go ahead and go to either Desmos or your calculator. And whenever you graph with Desmos, you do see that it is the bottom left and it is the bottom right. So it did work. Next, if you want to go ahead and pause the video, I try to do this one on your own and then hit resume to check your answer. What we're going to do here is we're going to factor out everything that we can. So on top, I was able to factor out a 4. And on bottom, this is going to factor into 2 parentheses. And now you're looking to see if anything cancels. It actually does not. This is an x plus 3 on top and an x minus 3 on bottom. They do not cancel. So there are no holes. Now you look at the vertical asymptotes. You're actually going to have 2 of them. So I'm going to set x minus 3 equal to 0. And I'm going to set x plus 2 equal to 0. So I'm going to get x equals 3 and x equals negative 2. So I'm going to go ahead and graph the vertical asymptote at negative 2 and go ahead and graph the vertical asymptote at 3. Next, horizontal asymptote. This is where you look at the highest degree. On top it's an x, but on bottom it's an x squared. Because it's bigger on bottom, it is going to have a horizontal asymptote of 0. Now, here's the only thing. This is going to be one of those rare cases that you actually may cross the the horizontal asymptote. There could be something near the origin to where you can cross the horizontal asymptote. So next thing I'm going to do is y-intercept. So we're going to take 0 and plug it in. So I'm going to plug 0 into my numerator, and I'm going to plug 0 into my x in the denominator, and I will get 12 on top and a negative 6 on bottom, which is negative 2. And then the x-intercept, this is where you possibly could have an x-intercept. So I'm going to set my denominator, I'm going to set my entire function equal to 0, and I'm going to cross multiply. So I'll get 0 times x squared minus x minus 6 equals 1 times 4x plus 12. 0 times anything is 0. Instead of equal to 4x plus 12, in solve, I'm going to subtract 12 and divide by 4, and I will get negative 3. So at negative 3, 0, it actually will cross the horizontal asymptote. This is, again, a rare case where this can happen. And now the domain. The domain is everything except vertical asymptotes and holes. So we have 2 vertical asymptotes. So it's going to be everything from negative infinity to, everything from negative infinity to negative 2, everything from negative 2 to 3, and then everything from 3 to infinity. The range is going to be everything except horizontal asymptotes and holes. Now, this is where it's different. Even though we do have a horizontal asymptote, we did realize that we actually crossed it, and so therefore the range in this case is going to be negative infinity to infinity. And now we're going to graph. Now this is where we are really not sure. We only have 1 point. We would need to do multiple points in order to figure out what's kind of going on. The best way for this case is to graph it. And when you graph, you have this interesting graph. So we saw that it crossed the x-axis here. And what happens is it crosses it, and then it looks like it is heading back towards the x-axis. On the right-hand side, it is at the top right, heading towards your asymptotes. And the bottom, and you actually have this very weird parabola-looking thing to where it does cross at 0, negative 2. So to graph, it looks like it is going to hit through the x-axis down and then actually head back towards. On the right-hand side, it is heading towards the asymptotes. And on the left-hand side, because of the y-intercept, it looks like it hit kind of this weird parabola heading back towards your asymptotes. So for the next one, again, pause the video, attempt to work this problem out, and then hit resume to check your answer. So on top, I'll get an x plus 1 times an x plus 3 to factor, and on bottom you have an x plus 1. And I notice that we will have a hole because something did cancel, leaving me with x plus 3 as the function to graph. So first there is a hole at x plus 1, so set it equal to 0, and you'll get x equals -1. And to find what the coordinate point is of that hole, then you plug -1 back into your final answer. So -1 plus 3 will give me a 2. So that is actually where I know that my hole at -1, 2, there is going to be a hole there. Vertical asymptote. There is no denominator after we canceled, and so we do not have a vertical asymptote. The horizontal asymptote, you look at the original highest degree. It is bigger on top, which means it is infinity, which means there is no horizontal asymptote. So actually, instead of hitting infinity, I'm actually just going to cancel it as a horizontal asymptote because we could say it is infinity. Y-intercept is where you're going to plug in 0. So I'll get 0 plus 4 times 0 plus 3 all over 0 plus 1, which will give you 3 over 1, which is 3. Or you could have plugged 0 into your final function. 0 plus 3 is 3. So I do know that it will hit the y-axis at 3. X-intercept is where I'm going to take, and I'm going to set this entire thing equal to, I'm going to set my final function equal to 0, and I'll get x equals -3. And so therefore at -3, 0 is my coordinate point. Now the domain is everything except vertical asymptotes and holes. And there is no vertical asymptote, but there is a hole, and we're looking for the x value here for the domain. So it's going to be -infinity to -1, and then from -1 to infinity. The range is going to be everything except for horizontal asymptote and holes, and it's the y value here. So it's going to be -infinity to 2 because the y value of the hole, and then from 2 to infinity. And then to graph, this is actually just a linear equation, so it is just going to be a straight line going all the way to infinity and -infinity. And last, we are going to graph this. First, there is nothing to factor, and so I recognize that there is no hole because there is nothing that canceled. Vertical asymptote is where you take the denominator and set it equal to 0, so you'll get x equals 2. And even this square, it just means that x equals 2 happened twice, but still, it's still just a vertical asymptote, which is a vertical line at 2. Horizontal asymptote, this is where you look at your highest degree. Think of this as an x to the 0 on top, and on bottom you have an x, which means the horizontal asymptote is going to be y equals 0. Because the higher degree is on bottom. The y-intercept, you're going to plug in 0 for x, and you'll get 4 over 4, which is 1. So this is the coordinate point 0, 1. So I'm going to go ahead and plot that point. The x-intercept is I'm going to set this equal to 0, and I'm going to cross multiply. So I'll get 0 times x minus 2 squared equals 4. 0 times anything is 0, so we get 0 equals 4, which 0 can never equal 4. So there is no x-intercept, which means we do not cross the horizontal asymptote here. The domain is going to be everything again except for vertical asymptote and holes. There is no holes, so it's just going to be from negative infinity to 2, and then 2 to infinity. And range is going to be everything except for horizontal asymptote or hole. Again, no hole. So you're looking for the horizontal asymptote. So it's going to be negative infinity to 0, and then 0 to infinity. And now there's a couple things because of this point, I'm pretty sure that it is probably going to be graphed this way, heading towards the asymptotes. Now, normally, these rational functions happen diagonal of each other. However, this is one of those rare cases to where it does not. Because of this square, I think it's actually going to hit in the positive on this side, because you square something, it's automatically going to be positive. So if I'm going to check, if I'm going to plug in 4, I'll get 4 over 4 minus 2 squared, which is 4 over 4, because 2 squared is 4, which is 1. So this is the coordinate point 4, 1, which means I believe it is going to hit on that side as well. Graph it just to make sure. And when you do graph it, you do see that on the left and on the right hand side, it is going to be in those places. Now, this case, we are actually given the different requirements, and we have to write original rational function. There are a million different possibilities for this, but you do have to make sure that the requirement is being met. So for example, I know it's going to be y equals, obviously, and I know there has to be a vertical asymptote at negative 3, which means x plus 3 must be in the denominator. But we also know that if we plug in 0 for x, we have to get a number of 2. So if I plug in 0 for x, we know that we're going to get a 3 on bottom. And so in order to get a y-intercept of 2, that means we have to have a 6 on top, because 6 divided by 3 is 2. So in order for the numerator to be 6, we could have a couple of things. We could literally just have the number 6, or we could have x plus 6, because if we do plug in 0, we'll get 6 on top and we will get 3 on bottom. Or it could be 2x plus 6 over x plus 3. All of these will all meet the requirements of what they told us. The vertical asymptote's at negative 3, which we have, and the y-intercept is at 2, meaning if we plug in 0 for every single one of these, we will still get a 6 on top and a 3 on bottom, 6 on top, 3 on bottom, 6 on top, 3 on bottom. So any one of these will represent our requirements. Next, we have a hole at x equals 3. That means that we had to have an x minus 3 on top and an x minus 3 on bottom in order for them to cancel to represent a hole at 3. The only other thing is that there has to be a horizontal asymptote at 2. So if we actually just put a 2 in front, I believe that will work, which means we will have y equals 2x minus 6 over x minus 3. If we look at the highest degree, they're the same, which means we look at the coefficients, and 2 over 1 gives us that horizontal asymptote. And if I factor out a 2, I will get x minus 3 over x minus 3, which will cancel, giving me a hole. So this will work. Next, we want our horizontal asymptote at y equals 1, and we have 2 vertical asymptotes. Well, therefore, we know that on bottom we have to have an x minus 1. Remember, because the factor is always opposite of the equals. And we'll have to have an x plus 4. So We know we have to have that, which means that is going to represent an x squared on bottom. If I was to FOIL that out, I would get an x squared. We're not sure what the rest is if I would have to FOIL it, but I know it's an x squared. So in order to get a horizontal asymptote of 1, since the denominator is an x squared, that means I have to have a numerator that is an x squared in order to be able to have a 1 in front and a 1 in front. So therefore, if I actually will just put an x squared on top, I believe that will satisfy because I'll have an x squared over an x squared, which will give me a horizontal asymptote of 1, and I will have my 2 vertical asymptotes. So you can either leave it like this, or you could FOIL, which would give you x squared plus 3x minus 4. Any others would have worked as well, meaning you could have x squared minus 10 over x squared plus 3x minus 4. Any of those would work because, again, the horizontal asymptote would still be a 1 and you would still have your vertical asymptotes.